Okay, awesome. Fun with fields. All we did in this class with fields was field axioms, right? We just listed out the axioms and then said proof stuff. We didn't talk about examples too much, right? We gave a couple examples. Can anyone give me some examples of fields? Just examples of sets that have operations that satisfy all those axioms. Give me examples. Okay, good. F2. I knew someone was going to say F2. Someone else is going to, that, and F2 is the set 0, 1, and the operations are given by a table. I'm not going to write down the table, but you know what they are. Somebody says R, good, classic normal example. What are the normal examples? Not every example of a function of a field has to be weird, like F2. There's some very simple examples of fields. Q, yeah. Kanishk is showing off in the chat. We didn't cover FP in general, so any subset of R, I see. Not every subset of R is a field. I'll write these down though. Z's not a field, right? It fails one of the axioms because you can't, remember in a field, you have to be able to divide, and you can't divide you can't divide by 3, right? Because 1 over 3 isn't an integer. You have to be able to take any element and find that its inverse is still there. So 3 has no inverse. So Z's not a field, but 3 does have an inverse in Q. Q is a field. You can check all the axioms. R is a field. F2, we talked about F3. That was the set 0, 1, and we called it X, I guess. We also talked about, and I have a table for you for later. This is a little thing I want to do later. I'll put it on the side. We'll come back to that. And another one, F4, we talked about. That was 0, 1, A, B. Okay. So here's a bunch of examples of fields, and I kind of put them into 2 columns here. There's the normal examples you've seen before, and here's examples that you haven't seen before. And so these examples, these second examples, these ones were hard to work with because the arithmetic was weird and unfamiliar, right? So what was weird about these fields? What was weird about these 3 fields? What property did it have that you saw and you're like, oh, that's really unfamiliar? Like F2, for example. What unfamiliar property did it have? 1 plus 1 equals 0, right? Exactly. That was weird, right? We're taught that 1 plus 1 equals 2, but there is no 2 in this set, and yet the set is supposed to be closed under addition. It's supposed to be that when you add 2 elements of the set, still the result is an element of the same set. So 1 plus 1 can't be 2 because 2 isn't in here for this field particularly. For Q, it's fine because if I add 1 and 1, I get 2, and 2 is still a rational number. So for Q, it's okay. If you define addition in such a way where 0 plus 0 equals 0, 1 plus 1 equals 0, this turns F2 into a field, and you have to define the multiplication as well. How about F3? Do you guys remember what property that one had? One plus 1 equals X, that's true. How about 1 plus 1 plus 1? That you can actually show as 0. 1 plus 1 plus 1 is actually 0. And 1 plus 1 is not 0. So there's a difference here, right? The first field, in F2, 1 plus 1 is 0. In F3, 1 plus 1 is not 0, but 1 plus 1 plus 1 is 0. So there's something you can do in any field, actually. Let me make some space to write this. In any field, you can always define, if F is a field, let's say, you can define the characteristic. This is a new definition for you. The characteristic of F is, we call it char F for short. It's N, where N is the least number of times you need to add, let's say the least non-negative integer. Well, let's say the least positive integer, such that if I add 1 n times, 1 plus 1 plus 1, and so on, n times, you get 0. Okay. That's the characteristic of a field. That's the word, the terminology that field theorists use. They call it the characteristic. So this, for example, F2, this field has characteristic 2. The characteristic of F2 is 2 because 1 plus 1 is 0. The characteristic of F3, the characteristic of F3 is how much? 3. What's the characteristic of F4? 4. Well, okay, to figure out the characteristic, here's what you do, right? You do 1 plus 1, you do 1 plus 1 plus 1, you do 1 plus 1 plus 1 plus 1, and you just keep adding ones, and then the first one where it's 0, that's the characteristic. So for example, if I found that 1 plus 1 was 0, then I can see that if I add 1 2 times, I get 0. So the characteristic would be 2. If 1 plus 1 plus 1 was 0, then the characteristic would be 3. If 1 plus 1 plus 1 was 0 and 1 plus 1 wasn't 0. So if this first one was non-zero, but the second one was 0, then the characteristic would be 3. So how can we find the characteristic? I have to figure out what 1 plus 1 is. Do you guys remember what 1 plus 1 is in F4? 0, 1, A, B. No, it wasn't A. You have to look at that table. The way the table was defined, 1 plus 1 was 0. 1 plus 1 plus 1 was 1. Right? Here, think of it like this. 1 plus 1 plus 1, I can write it like this. 1 plus 1 in brackets, and then add the next one. And this is 0. So this is like 0 plus 1, which is 1. So 1 plus 1 plus 1 equals 1. How about this? 1 plus 1 plus 1 plus 1, 4 times. That's 0. Why is that? Why is that 0? You guys can turn on your mics if you want. Oh, you have 2 1 plus 1s. Yeah, exactly. I can write the 1 plus 1s like this. 1 plus 1 plus 1 plus 1. And each of these is 0. So it's 0. So 1 plus 1 was 0. 3 1s was 1. 4 1s was 0. What about 5 1s? 1. So you see a pattern. 0, 1, 0, 1. So if I do 1 plus 1, and also it's getting annoying to write out all these 1s, you can actually call this 2 if you want. You can just call it 2. 2 is defined to be 0 in F4. 2 is defined to be 0 in F4. 3 is defined to be 1 in F4. 4 is defined to be 0. 5, well, it's not defined to be 0. It's defined to be 1 plus 1 plus 1 plus 1, which happens to be 0, and so on. So you can see 6 would be what? 0. 7 would be 1. 8 would be 0, and so on. In general, n is what? 0 if what? 0 if n's even. 1 if n's odd. So the characteristic of F4 is actually 2. Let's try to do something similar for F3. Let me make some space again. For F3, what do I do? Let's figure out what, well, 1 is just 1. 2 is 1 plus 1. 3 is 1 plus 1 plus 1. And I know I said, oh, wait a second, there's no 3 in this set. I'm defining 3 to be 1 plus 1 plus 1. Whatever that is, it is in F3. In any field, you can define an integer. You can always define in any field F, you define n to be 1 plus 1 plus 1 n times, if n is non-negative. So for example, 2 is 1 plus 1, 3 is 1 plus 1 plus 1. How about negative 3? What would I define negative 3 to be? It looks like F2 doesn't have any element -3, but I can define it and point out that -3 is one of these two elements. Which one is it? Ah, good. Alan got it. -1 plus -1 plus -1. See? You can define -3 to be the sum of three -1s. So F2 does have a -3 in it. F3 has a -3 in it. It's just not clear which one of these three elements is equal to -3. And -1 is also an element. In F3, -1 is x. So maybe I can write that x as negative, well, here, I'll cross it out. You can call that x -1. Okay, actually, let's not do it like that. Let's just say x equals -1. In F2, 1 equals -1 because 1 plus 1 is 0, right? And -1 is defined to be the additive inverse of 1. So 1, whatever you add to 1 to get 0, that's -1. And in this case, 1 is what you add to 1 to get 0. So 1 is its own inverse. That's not true in F3. In F3, to get 1, you need to add, in F3, you need to add 1 plus x to get 0. So the inverse of 1 is -x, and the inverse of x is -1. Sorry, I think I said that wrong. 1 plus x is 0. 1 plus x is 0, which means that x is -1. Or you could say -x is 1. Both of those are fine. Okay. So let's make that table again. Let's draw n. And then let's do 1 plus 1 plus 1. Well, n as an integer. Whoops, sorry. And then n as an element of F3. So for example, 1, I just call that 1. 2 would be 1 plus 1, which we can call x, and we know x is -1. So in total, 2 is equal to -1. How about 3? Which one of these three elements is equal to 3? Is 0, right? Because 1 plus 1 plus 1 is 0. How about 4? Whoops. 5, 6, and 7. Or sorry, 4, 5, 6, and so on. 4 it's 1. Why is that? Because if I write 4 out, it's 1 plus 1 plus 1 plus 1. And we already know that this first thing is 3. So this is 3 plus 1, and we know 3 is 0. 5 would be x. Remember, x is -1. 6 would be 0. And now you can see a pattern. 1, -1, 0. 1, -1, 0. So that's the field of three elements. We told you that x goes here, but I don't think anybody writes it that way. People usually write 2 here. Because 2 is equal to x is equal to -1. So nobody in real life actually writes F3 as the set 0, 1, x. We just did that because we didn't want to show you that there does have 2 in it. It's just that 2 plus 1 is defined to be 0 in F3. So the characteristic of F3 is 3 because what's going on here? Look, 1, 2, 3, the pattern has length 3. In F4, the pattern had length 2, right? 0, 1, and then it was repeating 0, 1, 0, 1, 0, 1. So it's the length of that pattern. That's the characteristic of a field. So car is represents, the characteristic represents the length of this cycle. If I do 1, 2, 3, 1, 2, 3, 1, or sorry, if I count the integers 1, 2, 3, 4, 5, and so on, I try to see which of those are 0, which of those are 1, and which of those are -1 or -2 or whatever else is in your field. It's just the least n that I get 0. In this case, the first time I get 0 is 3. It's So the characteristic is 3. In this case, the first time I got 0 was 2. So the characteristic was 2. So now we can make a different table. We can make a table of fields of n versus the characteristic of Fn. Or maybe I'll just write Fn. Actually, how about we do it like this? Let's write a field and then write the characteristic of that field. So for example, we just worked out the characteristic of F2 was what? Characteristic of F3 was what? F4. And then let's think more. Maybe there's an F5. How about F6? F7. But then we should extend our table and include the other familiar fields from before, Q and R. You guys want to fill in this table? What's the characteristic of F2? 2, yeah. What's the characteristic of F3? We said 3. Characteristic of F4 was 2. What do you think the characteristic of F5 is? 3. Well, not quite. It's not 3. Here's why. F2 is 0, 1. F3 is 0, 1, 2. F4 is 0, 1, 2, 3. And addition is done by wrapping around, kind of like here. I'll give you an example. I'll try to give you an example. Oh, actually, no, this is actually wrong. It's 0, 1, A and B. That was actually wrong, actually. It's not 0, 1, 2. Let me give you an example of what F5 is. Imagine you have a clock, 0 o'clock, like midnight, 1, 2, 3, and 4. Imagine you have a clock and it's 1 o'clock. And then let's say I want to do 1 plus 3. What I would do is do 1 and then move 3 hours over. So I would get 4. If I want to do 3 plus 4, I would start at 3 and then move 4 hours over. So 1, 2, 3, 4. 3 plus 4. 1, 2, 3, 4 is 2. If I want to do 4 plus 2, I start at 4 and do 1, 2. So 4 plus 2 is 1. If you use this table, you can easily do arithmetic in F5. This is an easy way to do arithmetic in F5. Now tell me, what's the characteristic of, this is just modular arithmetic. This is something called modular arithmetic that we're going to learn later in the course. We're actually going to do this in class, this clock stuff. So, okay, so what's the characteristic of F5? It's 5, right? Because 1 plus 1 plus 1 plus 1 plus 1, you need to add it 5 times. So the pattern is this, 2, 3, 2, 5. What's the characteristic of F6? 7, no. Make a clock. 0, 1. Also, I'm lying. I'm lying a little bit to you right now. Just say that in case there's any math people watching this who know that there's something very wrong with F6. So 0, 1, 2, 3, 4, 5. So this is, so you think it's 6, right? It looks like it's 6 if you believe the thing I just said about clocks. And what I said wasn't wrong. This is arithmetic mod 6. That's definitely correct. Like if I take 5 and add 2, that's 7. Mod 6, that's 1. Because it's wrapping around after 6 hours of the clock. If I do 4 plus 5, that's 9, which is 3, because it's 3 more than 6. Right? Here's the thing. F6, right? Okay, this better be a field, right? So what's the inverse of 3? Like the multiplicative inverse of 3. How do I find the multiplicative of How do I find the multiplicative inverse of a number? What's the multiplicative inverse again? How is that even defined? Yep, it gives you 1. Yeah, exactly. So I need to find a number x. So if I say, let's call it x, all I know is that 3 times x is equal to 1. So there's only 6 elements here. I can just check. 3 times 0, is that 1? 3 times 1, is that 1? 3 times 2, 3 times 3, 3 times 4, 3 times 5. I can just check all of them. Sorry, I skipped 4. Right? What's 3 times 0? 0. What's 3 times 1? 3. What's 3 times 2? That's 6. And 6, when you wrap around the clock, is 1, right? So 3 times 2 is 1. Well, let's write it as 6, which is 1. 3 times 3 is 9, which is what? 9 is mod 6, that's 3, because it's 3 greater than 6. 3 times 4 is 12. Mod 6? 0, because it's 6 more than 6. It's 6 times 2. Basically, it's the remainder when you divide by 6. So 12 divided by 6 has no remainder, so it's 0. 3 times 5, that's 15. What's the remainder when you divide that by 6? 3. Oh, and sorry, 3 times 2 is 6. I don't know why I wrote 1. That's 0. That's 0, right? I don't know why I wrote 1, because 6 when you divide by 6 is 0. So there's a pattern here. 0, 3, 0, 3, 0, 3. But what's going on? None of them is 1. What does that tell me? Three has no inverse in F6. So F6 is not a field. And since F6 is not a field, I shouldn't call it F. F stands for field. We don't call it F6. So that's what I was lying to you about before. We call it Z6 because it's integers mod 6. So if I go back up to that chart we were doing earlier, this isn't even a field. So maybe we'll get to Q and R later. Wait a second. Some of these aren't even fields. Which ones aren't fields? That's all messed up, right? How about F8? How about F9? I could be lying to you about any one of these now. Alan was saying something earlier in the chat about which of these could possibly actually be fields. Primes, maybe. If you do arithmetic mod, okay, yeah. So this is a subtle point. F7, so okay. F2 is just clock arithmetic mod 2, modular arithmetic mod 2. F3 is arithmetic mod 3. F4 is not the same thing as arithmetic mod 4. F4 is something else. It's not arithmetic mod 4. Let's try arithmetic mod 4, right? 0, 1, 2, 3. This is arithmetic mod 4. And in this case, I'll tell you now, one of these 4 elements doesn't have an inverse, and it's not 0. One of the 3 non-zero elements doesn't have an inverse. Do you guys know which one? Which element has no inverse here? Three. What's 3 times 2? It's 5. And what's 5 when you divide by 4? What's the remainder? Oh, 3 times 2 is 6. Sorry. Yeah, that's true. I don't know why I can't do math. I was doing 3 plus 2. 3 times 2 is 6. Right? and 6 is 2. Okay. How about 3 times 3? 9. And what's 9 mod 4? It's 1, because 9 divided by 4 is 2 times 4 plus 1. So 1's the remainder. So there, 3 times 3 is 1. That tells me that, so I don't need the first calculation. The second calculation tells me that 3 inverse is equal to 3. So 3 does have an inverse. 3 is equal to its own inverse. 1 is also equal to its own inverse. It always is. Multiplicative inverse. What about 2? What's the inverse of 2? Let's calculate. 2 times 1 is 2. 2 times 2 is 0. 2 times 3 is 6, which we worked out was 2. 0. Okay. Bye, Burgess. See ya. 2 times 2 is 0. That's what happened last time. There was a 0 here, and 3 had no inverse. If you can multiply by something else, something non-zero, and you get 0, then there's no inverse. And another way to see that is we just checked that none of the numbers in the clock multiplied to get 1. So 2 has no inverse. So what does that tell me? What does that tell me? Not a field. What's not a field? All elements must have inverse, not be, yeah, all elements must have inverses for a field to meet the multiplicative inverse condition. Yeah, it tells you that Z4 is not a field. Z4 isn't a field. Like this set 0, 1, 2, 3, that's not a field, but that's not what F4 is. F4 is something else. It's not Z4. That's tricky. So there is a field of 4 elements. It's just not Z4. Z4 isn't a field of 4 elements, but there's some other field with some other operations. F5 is Z5. F7, F6 is not Z6, but also there isn't even any field of 6 elements. Not only is Z6 not a field, also F6 doesn't even exist. There's no field of 6 elements. F7 is Z7. Yeah, Alan's getting the prime, the condition. It's when you have a prime number of elements. The field of P elements, if P is prime, is always just Z mod P. So I can erase the ones that don't count. So F11, I wrote Z9. I meant to write Z11. But there is a field of 4 elements, and there is a field of 8 elements, but there's no field of 6 elements. What's going on there? This is what's weird. Some fields are Z mod a number. Some fields exist, but they're not Z mod something. What's the character? What do you think the characteristic of F7 is? Yeah, I wish I can see why mathematicians are addicted to math. Yeah, when you see patterns like this, you just think, what's going on? How can I, what's the pattern? You just want to know, right? You have to know. You see something like this and you think, like, what's going on? Like, I'm actually genuinely curious, right? But we don't do stuff. I don't know why we don't do stuff like this in class. I have to get through all those polling questions. But okay, so how about F8? What's the characteristic of F8? Is there even a field of 8 elements? Can you even make one? Can you make a field of 8 elements? Maybe that it doesn't exist, just like F6, right? I mean, there was one of 4 elements, and 4 is not prime. Okay, at this point, I think it's actually really hard for me to actually tell you if these things exist without really getting deep into ring theory and stuff. But there is a field of 8 elements, and its characteristic is 2. There is a field of nine elements. Its characteristic is 3. There is no field of 10 elements. There is a field of 11 elements and its characteristic is 11. There is no field of 12 elements. See a pattern? What about F13? Here, let's do a couple more. This isn't what I wanted to talk about, but oh well, we were talking about it. F14, F15, F16, Zoe, no food, F17. And then maybe we should stop before we go too crazy. Which one of these? Okay, what's the characteristic of F13? What do you think? Do you think you can fill in the rest of the table? Give me the five numbers that fill in the rest of the table. 13. So as long as Fn can be composed of one prime factor, it has characteristic equal to that prime. Okay, you're seeing a pattern in the sequence. That's exactly correct. F14, there is no field of 14 elements. There's no field of 15 elements. 16 is 2 to the power 4, and so it has characteristic 2. 17 is a prime, so it has characteristic 17. Look at that table. Weird pattern, eh? But basically, there's no, there is a field of n elements. There's a theorem, actually. I could say that as a theorem. There exists a unique field. Zoe, no. Exists a unique field of n elements if and only if n is equal to some prime power. N equals p to the, let's say p to the k, where p is prime and k is greater than or equal 1. This is a theorem. And you might notice I used all the things we talked about in class, right? There exists unique fields, elements, if and only if. We talked about logical equivalence, right? This is why we're teaching you this stuff now, is so that when you see a statement like this, it doesn't freak you out. You see that and you understand what it's saying. It's saying there's a pattern here. There's a pattern in this table. And you can prove actually that the only time you can ever have a field of finitely many elements is when the number of elements is a prime power. I have to see what my cat's doing. Zoe, no food right now. Go to bed. Go take a nap. I don't think that's going to stop her. Oh, pretty cool, huh? Now, all of this were fields. All we were talking about now were fields of positive characteristic. This whole time we're talking about fields where the characteristic is 2, 3, 4, etc. Yeah, exactly. How does this extend to fields with infinitely many elements? Let's have a look. This is what we were doing before, right? Q, R, and Z, for example. Well, Z wasn't a field. We agreed on that. It's definitely not a field. So just Q and R. Those are like our only two examples of fields. Actually, would you give me 1 second to just plug in my computer? Okay, I'm back. So here's two, here are two fields. What, yeah, infinite fields. What's the characteristic of these two fields, by the way? What's the characteristic of Q? It's the least positive integer that when you add 1 up a bunch of times, you get 0. Can you even do that in Q? No matter how many times you add up 1, you'll never get 0 in Q, right? So you could say the characteristic is infinity because there's no number of times, but what people say is the characteristic is 0. So actually both of these fields have characteristic 0. These are both fields of characteristic 0. So what can you do with a field of characteristic 0? If you have a field, if F is a field of characteristic 0, it's going to be completely different from the flavor of math we were doing here. And there's no real theorem like this one, the one that we were talking about earlier. It's a completely different setup. It's a completely, totally different type of math. Well, okay, that's not necessarily true, but it has a very different flavor when you're working with fields of characteristic 0. If f is a field of characteristic 0, so with car f equals 0, there's a different theorem you can say. Then, how many elements do you think f has to have? These two elements were infinite. These two fields were infinite. You can prove that any field of characteristic 0 has infinitely many elements. Okay, so how do you do that? Well, I can give you a bit of a proof sketch for this. The other theorem I couldn't prove for you, but this one I can kind of try to prove to you, right? Well, definitely one plus, well, okay, I guess this is kind of I can just say it like this. 1 is an element of f, and therefore 1 plus 1 is an element of f, and I know it's not 0 because I know f is characteristic 0. So there's no way I can add 1 finitely many times and get 0. The same with 1 plus 1 plus 1. Same with 1 plus 1 plus 1 plus 1 4 times. All of these elements are in f. So you can, it looks like it has infinitely many elements, but I might be repeating them, right? 1 might be equal to 1 plus 1 plus 1. But if 1 was equal to 1 plus 1 plus 1, then I would have something like 1 equals 1 plus 1 plus 1, and then I could cancel the ones from each side. I would get 0 equals 1 plus 1, and that's definitely not true because I just said 1 plus 1 is not 0. So all these elements are distinct. So I've just listed out infinitely many elements. 1 plus 1 plus 1, remember what we call that? Whoops, let me make some space here. Remember 1 plus 1 was 2. 1 plus 1 plus 1, we defined that to be 3. That's the definition of 3. 4 is defined to be 1 plus 1 plus 1 plus 1, right? So if 4 is an element of f, by multiplicative inverses, that means 1 over 4 is an element of f too, right? So I mean, this proves the theorem as I posed it. But now we're noticing a different pattern. We're noticing that 1 over 4 has to also be an f, right? And if I add that twice, or maybe I can add that 3 times, right? 1 over 4 plus 1 over 4 plus 1 over 4. That's 3 over 4. That also has to be an f. I can get any fraction, actually, right? I can say, for example, 7 over 5. That's just 1 over 5 added by itself 7 times. And I know that 1 over 5 is 5 inverse. So if 5 is in f, then 5 inverse is in f. And I can add that 7 times to get 7 over 5. So this is also an f. Any fraction I want, I can just do this, even if it was negative. If I wanted negative 9 over 2, I could just take negative 1/2, negative 2 inverse, and add that up 9 times. And that's an f. So you can see that any rational number is contained in f. I wish we did cool stuff like this in class. If f is a field of characteristic 0, let's just write it like this. If car f is 0, where f is a field, then Q is a subset of f. Any field of characteristic 0 has to contain the rational numbers as a subset. So you can see it's infinite because Q is infinite, so it has an infinite subset. So f must be itself infinite. Okay. Let me show you a field of characteristic 0 that's not one of these two, because we've only seen these two fields of characteristic 0. Let's do examples, just like we did earlier, except for now field of characteristic 0, infinite fields. And that's where I'll get back to that in a second. That's where I made a little table and a little game to play here. Uh-oh, my cat. Zoe. Okay, I'll feed her. I'll be back in 1 second. Sorry about that. I have a little game here for us, a table. Here's what I want to do. And I'm going to wrap this back to fields of characteristic 0. We'll talk about that. But let's just do a little bit of number theory first and see the connection. I'm going to give you a number alpha. Let's just call it alpha, just some real number. And you have to find, or maybe a complex number. Let's add that to the table too, I. And you have to find a polynomial that has this alpha as a root. So for example, a polynomial with 3 as a root, a really simple example would be x minus 3. So this is a degree 1 polynomial. Okay. How about negative 3 over 2? Can somebody give me an example of a polynomial that has negative 3 over 2 as a root? 2x plus 3. Excellent. You could have also done, if you wanted, you could have also done x plus 3 over 2 if you wanted to really hack it. And the degree of this polynomial is 1 again. How about square root 2? Can you give me an example of a polynomial with that as a root? X squared. Close. I have to plug in root 2 and see if that has a root. Minus 2, exactly. And the degree now is 2. How about cube root of 5? X cubed minus 5. Nice. Oop, I have to go exactly at 11. How about the next one? This is tricky. This one's trickier. How about this? Root of 2 plus root of 3. I'll show you a trick. Let's call that number alpha. Oh, this is all our field stuff we were doing earlier. Let's call that number alpha. Root 2 plus root 3. Sorry, the square root of 2 plus square root of 3. What can I do to find a polynomial? What should I do to simplify this? Square. So alpha squared should be 2 plus root 3. Then maybe I'll bring the 2 to the other side. And now what should I do to simplify? Yep, square again. Exactly. And now, can you give me a polynomial with alpha as a root? Can you use what we just did? What polynomial would you give me? X squared minus 2, all squared minus 3. Excellent. X squared minus 2, all squared minus 3. Nice. And you could expand that out if you want. Yeah, you could definitely expand that out if you want, and I will not because I want to keep my sanity. Oh yeah, I didn't say this polynomial has degree 3. And this polynomial has degree 4, because when you expand it out, if you did, you don't need to expand it out to see that it has degree 4. You can just see it's x squared squared is going to be the biggest term. How about this one? Maybe you can do something similar. Call that number alpha and then do some math. Alpha equals square root 2 minus square root 3. What should I do in this case? Square, yeah. So I'm going to get 2 minus 2 square root 2 square root 3, I think, yeah, plus 3. Okay, the 2 plus 3 becomes 5. So this, I can write it as alpha squared minus 5 equals negative 2 times square root 2 times square root 3. Now what should I do? Square it again. Alpha squared minus 5 squared equals 4 times 2 times 3, right? Which is 4 times 2 is 8 times 3 is 24. I think I got that right. Then I subtract 24. So a polynomial here would be x squared minus 5 squared minus 24. Let me just get rid of that rough work there. And this is degree 4. And then how about this last one for I? It's not x squared minus 1. I squared is minus 1, so it's x squared plus 1. Because if you plug in I there, it'll be I squared plus 1. I squared is negative 1, so you get 0. So it's x squared plus 1, which is degree 2. Interesting. So let me take this table and see what point I'm trying to make when it comes to fields of characteristic 0. I'm trying to make a point. I don't know if it's clear yet. Let me ask you this. Let me ask you a completely seemingly separate question. What's the smallest field containing both Q, meaning I contain every rational number, and also containing the square root of 2? The smallest field, or just give me an example of a field. You could give me an example of a field if you want. R, yeah, the real numbers, but there is a smaller field than that. R has other numbers in it, like root 3 and cube root of 5 and all of these. The real numbers have all of these numbers in it. R has all of these numbers. But there's a smaller field that contains Q and the square root of 2 that doesn't contain those other numbers, not all of them at least. And it's this. We call it Q with root 2 in brackets to represent that it's the smallest field containing Q and root 2. And it's this. A plus B times the square. Well, here, let me tell you. Okay, before I give it, okay, I already gave it away, but maybe let's see it like this. Let's see it like this. If I had such a field F, let's say I had a field F that contains Q and it has root 2 in it as an element. Let's say I had a field like that. Well, then I would have to have, since it has Q in it, it certainly has 1 in it. And since it has 1 and root 2 and it's closed under addition, it would have to have 1 plus root 2 in it, right? And since it contains Q, it would have to have 2/3. And then I could say 5/4 if I want. And I can multiply that by root 2. And that has to be an F as well. And in fact, since it has both of these elements, I should be able to take these elements, and I know that F is closed under multiplication. So I should be able to multiply them together. And that should be an element of F as well. So before I even tell you what F is, you can figure out a couple of its elements, other than just rational numbers and root 2. 1 plus root 2, this weird combination of root 2, this weird product of combinations. And if I multiplied it out, I don't know why I made such a horrible number, but it's 2/3 plus 5/4 root 2 plus 2/3 root 2 plus root 2 times 5/4 root 2, which is 5/4 times 2, which is 10/4, which is also known as 5/2. So I can write this as 2/3 plus 5/2 plus, I just added these two numbers together and got this. Or, and for the second term, I can collect these 5/4 and 2/3. So I can write this as 5/4 plus 2/3, whatever that is, times root 2. I can factor out the root 2. This is some rational number because it's the sum of two rational numbers. This is some rational number. So this is equal to A plus B times root 2, where A and B are rational numbers. That turns out to be all you need to define this smallest field. You can define, that's what I was going to write earlier, Q root 2 as the set of all, as the smallest field containing Q and root 2, but you can actually say that it looks like this. A and B, all rational numbers, all real numbers of this form, A plus B times the square root of 2, where A and B are rational numbers. So for example, this one, this one, this one, and more, infinitely many. This is the smallest field containing Q and root 2. And you'll notice something here. To define an element of this set, I need two parameters, A and B. Let's say parameters in quotes, for lack of a better word, or two variables, right? Root 2. Degree 2. 2 parameters. Another pattern. See? Oh, good. What about the multiplicative inverse of root 2? Nice. That's a good question. What about 1 over root 2? How can you write that in this form? That's a good question. Whoops, sorry. Can you rationalize that? See? Square root of 2 over 2. This is 1/2. This is 0 plus 1/2 times the square root of 2. So it does have this form. And you can always do this. You can. I could have done the same way by rationalizing the denominator. I could have found the inverse of this element too. That's a good question. The fields have to be closed under inverses as well. How about q times the cube root of, or sorry, not q times, q, the smallest field containing q and the cube root of 5, let's say, because that's what was in my table earlier, cube root of 5. The polynomial we got was degree 3. There's actually no smaller polynomial. There's no small, you can't find a polynomial of degree 2 or 1. You can prove that. Maybe you're convinced it's a cube root. So how could I possibly square it and get a rational number, or sorry, and get 0? I say polynomial with alpha as a root. I should have said a polynomial with rational coefficients. We were just doing that naturally, but I guess that's a clearer way to say it. That is a more precise way. The way I said it, you could have given me this polynomial, x minus the cube root of 5. That has the cube root of 5 as a root, but it has an irrational coefficient. So I should have said with rational coefficients, because we're talking about q this whole time. Yeah. This field, you can prove that the smallest field containing q and the cube root of 5 is this: a plus b times the cube root of 5 plus b. Maybe I can write the cube root of 5 as 5 to the 1/3, and b times 5 to the 2/3. So I square it, where a, oh sorry, not b, I should have said c, where a, b, c are rational numbers. And you can see, again, I have 3 parameters this time. So you made a field that has a polynomial root, exactly, and q, exactly. We took a number that was a root of a polynomial, in this case cube root of 5, and we made a field out of it. So here's one last example before I have to go. One last example. How about pi? Can you give me a polynomial with pi as a root? Yeah, why did I write the degree? I'll show you in a second. How can I give you a polynomial with pi as a root? X minus pi, yeah. How about a polynomial with rational coefficients, though? Give me a polynomial with rational coefficients. Ooh. You need to describe pi in, okay, yeah. Yeah, and pi is not rational. He's saying you have to describe pi as a rational number. It's not a rational number, it's irrational. There's no way that you can write this as a terminating sequence of decimals or a repeating sequence of decimals. So pi is irrational. That's okay. Root 2 was irrational, and yet we found a polynomial. So it's not because it's irrational. It's because it's not algebraic. And I didn't tell you what that means. Well, I can tell you now what it means. It means that there's no polynomial. There's no polynomial with that property. And so we say that the degree of pi is infinite. So the degree of root 2, the degree of this polynomial is 2. So we define the degree of root 2 as 2. The degree of cube root of 5, since the polynomial, its polynomial had degree 3, we define the degree of cube root of 5 to be 3. Yeah, if I take pi to be 3, then I could just use the polynomial x minus 3. That's true. But then I'll take your grade to be 0. So there's no polynomial with pi as a root. So let's try to do this trick again. or this I don't know, this process where I take the Q and I add pi to it. I take the smallest field that contains Q and pi. How many parameters do you think they're going to be here? A plus b pi. What about pi squared? Can you write that as a plus b pi? What about pi cubed? What about 1 over pi? How can I write that out? Yeah, actually, that's a good one. How do I write 1 over pi? If I could write pi squared, here, I'll show you. If I can write pi squared as a plus b pi, then look what happens. Pi squared minus b pi minus a equals 0. So this is a polynomial with rational coefficients, negative b and negative a, and pi is a root of this polynomial. And that contradicts what I said earlier. There is no polynomial with that property. That's a theorem, that pi is transcendental. There's no polynomial with pi as a root. So I just contradicted this theorem, right? So this means that there's no way to write pi squared as a combination of lower powers of pi. And you can prove this in general. It's equivalent to proving that pi is transcendental, that there's no way to write these as lower powers of pi. No way. I'll just say no way. So how many elements are in here? Well, infinitely many elements in this set, but I need to include all rational numbers, and then I need to include pi and all rational multiples of pi. And then I need to include pi squared and all rational multiples of pi squared, pi squared, yeah. And so on until I just pick some n. I can't add infinitely many, so I end at finitely many terms. So I don't know, z times pi to the n. Maybe I should have given these better names. A1, A2, well, actually even better. Maybe I should have called this A0 plus A1 pi plus A2 pi squared, so that the pattern is pretty clear, plus AN pi to the n, where n is any number. Also, I need to include the inverse of pi. So I need that too. I need B0 plus B1 pi plus B2 pi squared up to Bm, let's say some other number, pi m. Here, n and m are non-negative integers, and all the ai's and bi's are rational numbers. So we didn't use this notation too much in class, but I think you know what it means. It just represents any combination of things of these forms. Like, for example, I could have pi plus 2 pi squared minus pi cubed divided by 1 plus 3 pi to the 4. This is an element of q pi, because it has to be. It's pi squared has to be in the field, pi cubed has to be in the field. Multiplying, fields are closed under multiplication, fields are also closed under division. So it has to contain this element. Just like what we did last time, it turns out that those are all the elements obtained by multiplying and adding pi together and then dividing all those as well. And you can see that I have an arbitrary number of parameters here, right? Like all these AIs. I can have n of them, and n can be anything. All these BIs. Arbitrary number of parameters. I gotta go too. So all that is just showing that this number theory stuff is connected to fields. When I have a number that has a polynomial, that's a root of a polynomial, I have a field that corresponds to a field with finitely many parameters. But if I have a real number that's not a polynomial root, it's not a root of any polynomial, that corresponds to a field with an arbitrary number with infinitely many parameters. You can't describe it with a finite list of parameters. Okay, so all that, I just wanted to show you some ways that number theory is connected to fields. Okay, I actually got to go, but I'll see you guys later.